What? So questions? Yes? I don't know. How many have you got till today?
11.
11. So going to be 12, I think.
What?
No? No? Well, it actually depends on your TA. You should be nice to them, and then maybe there'll be only 11. It's completely in their hands.
אוקיי, אז בוא נהיה נחמדים אליהם כולם, חבר'ה, אנרגיות טובות. שחבר של, קדימה.
Alright. So, we're still in the Ising model. Well, it's actually the last thing that we're going to do. And if you remember, we also will discuss the interrogando starting today. So if you remember, we found a solution in the mean field representation. So if we plot here, this is our M, and this is hyperbolic tangents of beta, right? So what else? J tilde and M, right? This is what we have right here. So this is the straight line, which is basically M. And we have found that when the temperature is lower, it's lower than a specific critical value, okay, we have additional two solutions. Okay, let's call it plus M0, and here we have minus M0. Minus M0. The critical transition, when we have three solutions to this, so our equation was M equals to hyperbolic tangents of beta J tilde M. Okay. So below for T, below TC, there are three solutions. And for T above TC, one solution. M equals 0. Okay. And this TC, okay, and this TC was equal to J tilde over K Boltzmann. Okay. TC. Now, let's try and see what exactly this means, and we started to represent everything by the means of the free energy. Right? So our free energy, I will remind you, was F was minus 1/2 M squared J tilde, right? And here we had, remember, we had over there, this is our free energy. So this was plus, and here was minus 1 over beta, log of 2 hyperbolic cosine of beta J tilde M plus mu 0 H. Right. So
מה השאלה שמה במונה של הדבר הזה ששווה TC?
TC equals to J tilde divided by K Boltzmann. This is what we thought. All right, so let's see how this function behaves as a function of M. Right? And remember, this was an important quantity, the properties of this function, while we use that, well, this equation, M equals to tangents, hyperbolic tangents of beta J tilde of M was obtained for H equals 0 from this condition, dF to dM equals to 0. So we have a free parameter, right? This is not the this is something about the system that we don't really know. The system has to choose M wisely, how it chooses m wisely. We know that the free energy should be at minimum in an equilibrium. So we use this criteria, then we obtain this equation. From this equation, we observe that, well, there is a transition from one solution to three solutions. Okay, and this happens exactly at this critical temperature. Okay. Now let's look on what exactly happens to this free energy. Okay, when we plot it as a function of m0, what happens to this function? So let's start from sufficiently high temperature. So we are at T larger than Tc. Okay, we are at T larger than Tc, and we are at H larger than 0. Okay, so this is the condition that we start with, and we know that the system has to be paramagnetic, right? But we have a non-zero external magnetic field. Okay? So if we took this, we take this and we plot it. Okay? So what we would obtain, so this is f as a function of m. It looks basically, if the temperature is high enough, it looks basically as a kind of a parabola. Okay? So we see we have a non-zero, small non-zero minima, a non-zero magnetic m, which occurs due to the fact that we have a positive external field. So what is happening? We have an external field. Due to this external field, all the different spins, they prefer to point in the direction of the external field, right? So the minima of the free energy, it occurs at some specific non-zero or positive m, right? So we have, by looking on this function over here, we know, well, yes, we indeed should observe something which is not zero, some magnetic moment of the system. We apply, and this is reasonable, right? We apply an external field, and this external field causes a specific preference, a directional preference of the spins, and they point in a specific direction, and then there is a net magnetic moment. Right? So, if you remember this plot of average m as a function of temperature, and usually we plotted it like this. So we are sitting somewhere here, but this red plot is for what? Is for zero external field, right? 0H. Now what I have done, I said, well, if we do have an external field, what's going to happen? Well, due to the external field, and we look on the minima of the free energy, what we know is what? That there should be a specific magnetic moment. So if we have, so this is for h equals 0, if we have h greater than 0, then this line is basically will look like this. Okay? This line will look like this. So there is a small non-zero magnetic field which occurs due to what? To the presence of this h. The higher the h is going to be, the higher this specific behavior of the net magnetic moment of the system is going to be, right? So there is some sort of response. I apply a stronger external magnetic field. The response of the system, which is what? Which is the self-magnetic moment, is going to be higher. Okay, so the larger the h is, basically the larger this line is going to be over here. Okay. No, we're going to see what exactly going to happen at Tc. Right? So what's starting to happen at around Tc? Right? So around Tc, you can take this formula, plot it in Wolfram, for example. Okay. So what we're going to have, this is m, this is f, h is larger than 0, and t is equals exactly to Tc. Yes?
למה לנו קבוצה בנגזרת שיש h?
So what is going to h what's the problem with H? We still don't know what's happening over here. Nothing bad happens.
למה זה בכלל עולה? למה זה לא ישר? למה זה לא קבוע?
What do you mean?
פה זה, האדום זה 0.
Alright, so the question is why this blue line is actually rising up as we go to smaller and smaller temperatures. So first of all, what you would see that as you plot this function, you simply need to plot this function, right? And you will see that all this parabola, as a function of temperature, will be shifting a little bit to the right. Okay, so the position of this minima as a function of temperature for high enough temperatures is simply shifting to the right. What it means? It means that the self-magnetic moment is actually going up. Right? So this is a mathematical result. So what I have plotted to you over here, that this function, blue line, is going up is due to the fact that the minima of the free energy is shifting to the right with the temperature. As I lower the temperature, this M is going towards more and more to the right. Physically, what happens? We are getting closer to this critical point. And something interesting is going to happen at the critical point. We know that even when there is no external magnetic field, right, there is a self-induced magnetic moment for the system. It's becoming a ferromagnet. Right? So there is going to be a net magnetic, self-magnetic moment, positive or negative, when we are at this point, even if there is no external magnetic field. Now, the external magnetic field will only amplify this behavior. Right? This is why this function is going up. This is a hand-waving argument. The argument is, well, because this is the free energy, and the free energy behaves in such a fashion that this minima, as you go towards TC, is shifting to the right. This is mathematically why it's happening. And hand-waving argument, well, when you don't have any external magnetic field, you have self-induced magnetic moment, and due to the presence of external magnetic field, you should have something bigger, because you have more preference now to go to higher magnetic moments, right? Because you push the system in this direction. Even if you do not push the system in this direction, it's going to be here. Now, if you push it, well, probably it's going to be somewhere higher, right? Because it has some sort of incentive to go to higher magnetic moments. Okay? But again, the explanation is mathematical. Yes? No. So the previous lecture, we discussed only when H was equals to 0. Right? And now we are digging. Both of them. You have several parameters here, right? You have this function. It depends, well, J tilde, let's assume it's constant, right? So what you have here, mu0 is constant. So you have two parameters you can control, two knobs. One knob is the external field, the magnetic field. The other is beta, which is temperature. You can turn both of them or separately. Both of them affect on the shape of the function. Okay. So what starts to happen over here when we are getting closer to TC? As I told you, there is still some minima over here. Okay. But it looks more like this. Right? It starts to look, instead of simple parabola that looks like this, right? At t equals Tc, we start to see some sort of local changes that occurs in the vicinity of m equals 0. We still have this first minima that we observed previously, and it even shifted a little bit to the right, right? So you still have a rising function, but there is something else that starts to occur on the left-hand side. Okay. This is just plotted in Mathematica, and you will see.
The pitul.
Sorry?
Pitul.
Very not exact. Close.
Minimum.
Okay, so where it's not exactly. It's not exactly a point where the derivative is 0. But we do know that if you lower the temperature even further, right? So if you lower the temperature even further, what will happen? There is going to be, we have to go below PC in order to observe as additional minima that occurs over here. Okay? So if we now go to t below Tc, and we plot f as a function of m, we start to see double well function. Okay? So it looks like this. Okay? And h is positive. Okay? Nothing bad happens afterwards, so this is the whole behavior. You start from something that looks like a parabola, then something weird start to appear around t equals to Tc, right? And as you go below, well, there is only an additional minima that appears on the left-hand side. This basically means that this function will continue to rise up, and nothing bad is going to happen to this magnetic moment. Yes? Questions?
Does the magnetic moment will be higher just, המומנט המגנטי הגדול רק בתוספת של H?
Yes, only well, exactly by how much you have to calculate. Okay. Not exactly by H, right? You have to exactly calculate it from the function that I erased, okay? But it's going to be higher. Why? Now, physically, I'm explaining is you have a preference. You're going to obtain a solution A, or you have somebody who is pushing you in this direction, and so of course you're going to overcome A. That's it. By exactly how, you need to calculate. It's not exactly by H. Right?
Does that mean no phase transition?
Sorry? So what is a phase transition? So nothing bad happens. Absolutely nothing bad happens to the system. The system was ordered, you see? The system was ordered here. Why it was ordered? Because there was external bias that was pushing the order in a specific direction. It was ordered over here, it was ordered over here, this ordered over here, well, and it's still ordered over here. So when we apply an external field, there is no phase transition. Everything is smeared out, right? So we do see that there is some sort of a rise up that appears over here, but the transition is smeared. So this specific point that we observed before, that it was 0 and then non-zero afterwards, it's absolutely smeared. Right? Now, the appearance of additional minima, why there is no transition? Because the appearance of an additional minima, okay, remember that what I told you about how you should use the free energy? You think about it exactly as you think as some general energetic potential in mechanics. The system always wants to sit, or how we see the system is a particle that sits at the minima of this external, potential of the system. That's it. So if you describe, if for some specific point in time, the system had a magnetic moment which was higher, what eventually will happen? There are effective forces that will drag the system towards the lowest minima of the free energy, and it will sit there. It will, due to some thermal fluctuations, because there are thermal effects. The temperature, the spins they can flip up and down. There are probabilities, right? So due to those fluctuations, the particle or the system can rise a little bit to the left or to the right. It can change momentarily its magnetic moment, right? So if we look on the system as a function of time, for this specific case, so this is m, this is time, so there is the specific m0, and it fluctuates around it. Okay? Now, this is not noise because we cannot simply calculate, or our experiment is noisy in the sense that the equipment is not good enough. No, all the different spins, they are picking directions and they're flipping from up to down, or at least some of them, and this causes this m to go a little bit up or to go a little bit down. It's like a particle in this potential that is shifting to the right and shifting to the left. Okay? But there are effective forces that always driving it towards the minimum of the free energy. Okay? Now, what happened? Why we don't see any phase transition over here? This is what I described. We had a parabola, we have this guy, right, which I don't know how to call it, and we have a double well description. The second well, this one, is higher. Right? It is higher, so it's not a preferable state of the system. The system does not want to sit over here. Okay? It prefers to sit in this position. Yes.
If you look at it in the same way as classical mechanics,
Yes.
if you place the system inside of the small well, it will stay there.
No, because it's not classical mechanics. Because there are thermal fluctuations. In classical mechanics, if you put a system in a specific position, it will not move, right? Because you can say, well, I have a zero kinetic energy. Here, the kinetic energy, 1/2 mv squared, is 1/2 k Boltzmann T. So you always have thermal fluctuations on average. So the system, if you put this particle over here, it will jiggle around, as you say, it will jiggle around for some time. But after a while, and we are not concerned ourselves with how much time it will take, but after a while, it will get a high fluctuation and will get kicked out of this well, and eventually it will come towards the lowest flow. Right? And it's possible to calculate exactly how much time it's going to take it, but eventually it will happen. Right?
Shouldn't take the analogy to classical mechanics.
So not over push it. Okay? Because here there are friction, okay, there are thermal fluctuations. The only thing that you have to remember in mind is that the equilibrium is defined by the lowest minimum. And when you have a non-zero flow, there are effective forces that drag you toward the minimum. Those additional minimas, they are not stable states. So the global minima is called, this is a stable state. The other minima, they can also be stable. Why? Because there are no net effective forces that apply to the system. But they are called metastable. Why they are metastable? Well, if I put my particle over here, let's assume that this is the behavior that we want. We put our system in minus m0. Okay? So we're starting from this position. The particle jiggles around. So this is the noise that we've seen before. After a while, it will get a kick somehow. Okay? This is a non-equilibrium process. It will get kicked to the plus m0. Okay? And will start to jiggle again over here. And will probably stay there for extremely long amount of time.
זה אומר שם מעבר פאזה?
It's not a phase transition.
למרות ש...
No, because it's a function of time. You live the system, and eventually, after a while, it will reach the global steady state, and it will sit there. Okay? But it's not a phase transition. The transition from here, there are some dynamics that occurs, and there are time scales that will take the system to cross this energetic barrier, because this is F, it's free energy, so this is some energetic barrier that the system has to cross. But this is not a phase transition. Right? This is a temporal modification of the orientations of the spins. Because if you look on a specific spin, so you have a system, right? You have a system, and there are a lot of spins. And you focus on single one of them. Just one, pick one. Because what we know that there is a probability P up and there's a probability P down. Okay? What it means, so it's not that when we're sitting here that the probability P up is 1 and the probability P down is 0. No, it is not what's happening. The probability P up is still less than 1 and the probability of P down is still greater than 0. So the spin, as a function of time, it will stay in a specific position, but from time to time it can flip. What does not happen is that huge chunks of the whole material spontaneously change their position. So it can happen to single spins, but it will, when it's in stable situation, it almost never happens to the whole material. Right? So this is something that we have to bear in mind. Single spins, from time to time, they can change their direction. The whole material, probably not. Exactly. So there are small fluctuations that are happening on single spins, but there are almost no fluctuations, or there are extremely rare fluctuations that can take you from this position to that position. Okay, we can calculate, so it's not part of this class, but one can calculate how much time it will take you to go from here to there, and it's going to be a huge amount of time. Yes?
אם אתה מעלה את H עוד, אז זה... כאילו, איפה נמצא הזרוע השנייה של הכחול הזה?
Okay, so there is a maxima. What is the maxima? When all the different spins are pointing up. There is no higher magnetic moment than the magnetic moment when all the spins are pointing up. And that's it. This is your maxima. You cannot push H higher than this specific value. Okay? Think about it. What is a magnetic moment? How we measure it?
אני יכולה, אבל זה לא
No, it won't help you. The magnetic moment is mu0 sum over I SRI. Okay? So this SRIs can be either +1 or -1. Okay? So M maximal. M equals to mu0 multiplied by N. That's it. You cannot push it more than that. It does not matter what is the size of your external field. Right? Because you measure the magnetic moment by the amount of spins that are pointing in a specific direction. And the amount of spins is limited, so the magnetic moment is also limited by the size of the system, right? If the system is extremely large, so of course there is no limit. Usually your system is limited. Yes?
A few questions. One, if H is smaller than 0.
I'm going to this.
Okay.
In a second,
Then
yes.
the second one, does the magnetic moment of both the metastable and stable state are the same, but just...
Not exactly, no. So, no. The answer is no. The answer to the second question, so this is not, well, I plotted here plus m0 and minus m0, but it's actually wrong. So this is 1 and this is 2, and they are different. So you have to solve exactly this, you have to find the minima of the free energy in order to answer this question. Okay? They are no symmetric when the external field is not 0.
Yeah.
When the external field is 0, they are absolutely symmetric, as we've seen. Yes?
ממש קטן. אם אנחנו נסתכל על הגרף הכחול, הרציף, אז אם אנחנו נסתכל על הברנץ' שאמור לרדת למטה, הוא אמור לחתוך גם את הגרף האדום? כי...
Oh, we will see exactly in 1 second what happens when we're going to the other solution, right? So the question is what's happening when we're crossing from here to there. We will see in a second, right?
למה יש לנו עוד קו מקווקו פה מעל הקו?
So this is H, and this is if you take a little bit higher, external field.
זה לא כמו שעשינו פה אבל למטה עם
No. So this is if you take even higher external field is going to be like this. Okay? And even higher it's going to be like this. So as a function of H is going up, but what Eden asked me is it's actually going to be limited.
ולמה היינו צריכים פה את ה-P up ו-P down? זה הסתברויות.
So this is already an example, other example. Alright, so what happens if if I'm in the negative H, right? So for example, I'm sitting over here. I'm below PC. So the free energy is described by this. Let's make some iterations. So this is my free energy. This is my starting point. And what I'm starting to do is the following. I'm starting to push my H towards 0, right? I'm starting to decrease my external field. It was whatever, but positive, and I'm pushing it towards 0. So first of all, as I told you, this point over here is going eventually for H equals 0 to reach the solution of the zero field Ising model, right? So as I'm decreasing H, eventually to reach this point over here. Right? So how will my free energy look like? So this is the free energy as a function of M. So T lower than PC, H equals 0. So as you told me, it has to be symmetric. So we're going to have symmetric double well potential. Okay. Now, my system was sitting in this well, it will continue to sit exactly in the same well. Okay. So remember that I told you, well, we have two solutions to the equation. How the system picks up, and I explained it to you, well, it depends on the initial conditions. So the initial conditions can be determined by fluctuations, or they can be determined by how exactly I'm taking this limit of h goes to 0. So what I have done over here, I've taken h to 0, but from the positive sign. So this is h go to 0 plus, right? So what happens? This free energy, eventually it was not symmetrical. There was a stable state and metastable state. And eventually it reaches a perfectly symmetric situation when the two states are symmetric. Okay, and the system has to pick up, because sitting here is exactly as sitting over here. But the initial conditions, because we started from positive m, we can only reach the positive m solution. Right? So this is how the system picks up. We start from h, which is non-zero. We decrease it towards the solution where h is 0, 0 plus, and the system has to converge. It cannot, it wasn't sitting over here. It was already sitting in this well, so it will keep sitting over here. Okay. So this is great. Now, what will happen when we'll decrease h below 0? Exactly. There are no additional solutions in all this region. This is a forbidden state over here. So when we decrease h to below 0, what will happen? That it will jump to the next solution, which is the other branch of the solution that we found previously. Right? So why it appears? We have to take this plot and reverse it somehow.
But if I'm starting from h equals 0, where does the system pick?
So it picks on its initial configuration. How exactly you brought the system to this point. If you brought it from u to h, it's going to pick one of the solutions because you were already sitting there. I will discuss again what happens if you bring the system to 0 when it was sitting. This was a symmetric parabola and we're sitting exactly in the center. Okay, so we have f, and we have m, and we have t below tc. H is lower than 0. And now we have something that looks like this. So what's going on? The system, we started from this point. It was sitting at this well, and it was sitting at this well on the right hand side, so positive net magnetic moment. And now, because we lowered the external potential, external field, a little bit lower than 0, so it's still sitting in this well. But this is now, instead of stable, this is a metastable state. Right? Metastable. So what happens to the system in a metastable state? Eventually, it will cross over here and jump pretty fast to the stable state. Okay. So this is a jump. We lower h, we take h, it crosses 0, and we have a finite jump in the net magnetic moment. It's not a small jump. Big jump. Right? It's proportional to the size of the system. So what we observe over here, as a function of h, what we observed over here, a phase transition. Which order?
Second.
First, right? There was, so what we had, this is our line. We started over here, we decreased h, we decreased h, we decreased h, we reached a specific h, with a specific net magnetic moment, which is not 0, at h equals 0. We shift our h slightly to 0 minus epsilon, right? And the system, whoops, jumps to the other side of this diagram. Right? So this is a finite jump, and finite jumps occur for first order transitions, right? So this is what exactly happened. Our state, instead of being a stable, suddenly became a metastable, and the system had to choose a new state. And the whole system will somehow, it will take time, but it will flip and will cross to the stable solution. Yes?
You didn't see this in the graph for the hysteresis.
All right, so great question. We will come to that in a second. What happens for the hysteresis? Because I cheated you there a little bit, right? A little bit. The hysteresis loop is correct, but it's a dynamic loop. It's a dynamic loop. And the size of this loop, it depends on how fast you're modifying your external magnetic field. So, exactly. This is the hysteresis loop. It depends on how fast, because you sweep the external magnetic field. You change it from 0 to some high value, and then you go backwards. And you do it in a specific rate. And if you do this extremely, extremely slowly, your results are going to change. How slow? Depends on the material. Some sort. I will plot it. All right? Okay, so we have here now, if you think about it, as a function of h, we have a first order phase transition because we're performing this finite jump, okay, for the free energy. We're crossing from stable to metastable state. Now we can go backwards, right? We can say, well, what will happen if we will reverse now h, right? If we will reverse h, we're sitting over here. We are going to cross, we are below the critical temperature. We approach h equals 0, so this free energy becomes symmetric. But the system is already sitting on the left-hand side, right? It's sitting on the left-hand side. So it's still going to sit on the left-hand side here.
So it's going to stay there.
It will, because it would like to stay here. So it will stay there, right? And only if you take the high enough external magnetic field, this asymmetric or this symmetric shape will turn into an asymmetric shape, and the system eventually will cross from this metastable to a stable situation. Right? So what we can see is that if there is a finite change of where these stable and metastable solutions appear, then we see a first order phase transition. Right? So as a function of h, we do know that there is a phase transition because there is a finite jump in the magnetic moment. As a function of temperature, it's different. Right? So as a function of temperature, if we take h equals 0, there is a critical point at Tc. Only at Tc we have a non-zero. We have a zero magnetic moment, and then suddenly a new solution starts, either positive or negative, right? And we are choosing this additional solution, so there is a net magnetic moment. So the transition as a function of t for h equals 0, there is something special about this point, but there is no net jump. Right? So this is definitely not a first order phase transition. And also, if we take h, which is positive or negative, right? If it's negative, it's going to be like this. If we start in this point and h is not equal, h is positive, and we modify our temperature from higher temperatures to lower temperatures, nothing really bad happens on this slope. It's a continuous transformation, right? Because, well, as we seen before, we started on a parabola, and then we have some asymmetry that it's occurring, and eventually we have this deep well. But nothing bad happens to the system. Only when h equals 0, only at h equals 0, something peculiar occurs. Why I'm saying that only at h equals 0, there is indeed something peculiar. Because we've seen what appears for h equal positive or h negative. There are two minima, and one is deeper than the other, and the transition occurs exactly when they're equal. Okay, and we shift this external parameter to the left or to the right, and then one of the minima wins, and the system chooses. So this is why there are a finite jump. But what happens on this red line when h exactly equals to 0? So we start at higher temperatures.
אז שאתה אומר שיש מעבר פאזה מסדר ראשון עם H הוא לא אפס, אז זה של F או שגם ביחס ל-M?
M. The order, so what is, how I describe here a phase transition. A phase transition, something jumps. What is jumping over here? The magnetic moment. Okay? So what I do calculate, or what do I observe? What is my observable? My observable is the magnetic moment. And the magnetic moment is basically going from jumps from a positive value to a negative value. This is why it's a first order phase transition. As a function of temperature, it's going to 0 to non-zero, only over here, only for H equals 0. For positive H, it's always positive, well, it's growing, nothing bad happens here. And for H negative, it was always negative, and it was decreasing. Nothing bad happens.
אבל זה לא קפיצה?
This is a jump. Okay, so this is a jump.
לא, ב-F זה לא קפיצה מהמינימום למינימום?
This is a jump. This is how I describe the jump. That there was one, this is the deepest minima, and then another minima appears.
יש גם מעבר פאזה ביחס ל-F או שהוא רק...
No. F is, well, it's continuously changing from one shape to another.
Okay.
Nothing bad happens to F. F is a continuous function. You can take as many derivatives of it as much as you want. Like in mathematical terms, it's C infinity. Nothing really bad happens to F. What happens, bad, right? It's not bad, it's natural, is that one minima becomes deeper than the other one. And the system chooses one of the minima. This is why we see this abrupt change in the properties in the magnetic moment. So, what is F as a function of M? And we are T above Tc, and we are at H equals 0. So this is a perfectly symmetric parabola. All right. Okay. So this is H equals to 0. What happens if we continue to this H equal to 0, but T goes below Tc, or T equals to Tc? T equals to Tc. So we started at this point, we started over here, H was 0, and we're taking the temperature down towards the critical temperature, towards the Curie temperature. Okay? So this is F, this is M. And remember, nothing bad happens to this function. So it had one minima, and exactly at 0, at t equals tc, it still have one minima. But it's not only the first order derivative is 0, it's also the second order derivative is 0. Okay? So this is a critical point, or some point which is of higher order than just simple minima or maxima. So it's becoming much more flatter than the regular minima, because also the second order derivative at m equals 0 for t equals tc and h equals 0, it also 0. So we have still some function that look like this. Right? So just this minima becomes broader, but there is still no additional minima. The only minima that the system has, it's at 0. Right? Yes?
So no.
Okay.
It just obtains a different shape, but it's the same.
But it's the same minima. But the shape is becoming a little bit broader. So you have the first order derivative of 0, and also the second order derivative is 0. Mm-hmm. It was negative, right, beforehand, and now what I'm saying, take the second order derivative at m equals 0, it's still 0. Okay? But nothing bad happened to the function. There is no additional minima. Okay? The transition is smooth. But what happens immediately afterwards? When h is 0 and t is lower than tc, we know that this broad function will start to develop two minima, right? Symmetric minima. So the function, or our system, was somewhere over here. and it had to choose either to go to the right or to go to the left. How it chooses? Exactly. So it's according to the initial conditions. If we look on m as a function of time, so it was fluctuating. Over here it was at 0. Over here it was at 0. But what happened? Because the system became a little bit broader, it's less confined. So there were some fluctuations over here. The particle or the system was jiggling to the left and to the right. Now what starts to happen over here, exactly over here, is that the system can now go more to the right and more to the left. Why? Because the slope of the system became lower. The slope of this function is the effective force. Remember, it's exactly as in classical mechanics. The slope of the system became lower, so the fluctuations can become larger. What actually happens is that those fluctuations exactly at critical temperature is driving the system more to the right and more to the left. So if you look at the function of time, it was fluctuating. This is T higher than Tc. We switch the temperature and we get the temperature below this. So we start over here and so this is our original point, and we kick our system into this region. This is T. If beforehand we shifted the system from up to down by modifying H, now we're shifting the system from left to right or right to left by modifying temperature. Okay, so at this point, exactly at this point, T equals to Tc. T is smaller than Tc. And here, T equals to Tc.
זה ציר זמן?
This is as a function of time.
למה הטמפרטורה משתנה?
Because I'm modifying it. We started over here. The temperature was high. Then I shifted the temperature and shifted it towards T equals to Tc. So the system was jiggling to the right and to the left. And if I'm looking on it as a function of time, there were some small fluctuations. What? T, yeah. Thanks. Then so the system was over here. This is the upper plot. Then I brought the system into this critical temperature. What happens at critical temperature? The system is still binding. There is still only one minima at 0, but the slope is shallower. So the forces that try and keep the system backwards towards 0 are less important. What basically happens is that those fluctuations, they become larger. No. They're constant because I'm keeping the temperature constant. They're not growing as a function of time. They're just bigger because there's more space to move. Okay? And then I take the system from this critical temperature to a lower temperature when T is lower than Tc. T lower than Tc. The system was somewhere over here. Okay, somewhere over here means that I caught the system exactly at the point on time when I shifted the temperature from critical temperature to a temperature lower than the Tc. It was somewhere over here. Okay? So the system was sitting here exactly at the time when I shifted my temperature, and now the general potential is not like this. It's not symmetric. In a sense, there is not only one single minima at 0. So at this point, when the system was sitting over here, I shifted everything, so miraculously, I made my effective potential into a double well. So the system was sitting over here. Or, I'm sorry, somewhere over here. Right? Because I made this change. The system was fluctuating around 0. The system is still fluctuating around 0, but somehow I managed to change the temperature when the system is on the right-hand side. So at T equals 0, the system is over here. And now it's going to choose the right-hand side minima. It's going to come over here. So I'm started over here, it's going over here, and then it will fluctuate around a new average value. Yes. This? Okay. It's usually there is some at t equals exactly zero, it should converge exactly to the same value. Exactly at zero. All right, so those are the transitions, but you see what happens. First order transition, we have a finite jump when there are two minima. Right? So the only thing that matters in order to describe first order transition or second order transition or whatever, first order transition, the system was sitting in one stable state and the other metastable state somehow became more important, and the system is crossing this barrier and turning into the new stable state that appears. And this transition appears on finite length, so there is a finite jump. This is first order transition. This is what we have seen when we're crossing h from positive values to negative values. The second order phase transition, what we described over here, is we had only one single metastable state. Only one. And this one single metastable state split it into two not meta. We have one stable state, and this stable state split it into two additional stable states. And on its own, it became what? It became unstable, right? Because the center now, it's unstable point. So what happens? There is no finite jump. Why? Because I have created a new additional stable state, which is located extremely close to the old stable state, right? Because if you think about it, exactly at t equals 2tc, all of those three there are two minima and one maxima, they are all concentrated exactly at the center over here. So this is why the transition is continuous, but there are still, and we will see this in half an hour maybe, there are still some additional, not constraints, but there are some additional effects. For example, if we will cross this line and we take the derivative of m with respect to t, we will see that it's 0 over here and it's not 0 over on the left hand side. Right? So this is also why it's called second order. The observable itself does not perform any jump, but its derivative is going to perform a specific jump. Yes?
Can we also see these phase transitions in higher dimensions? Like are there two-dimensional phase transitions?
So yes, if your order parameter, for example, is two-dimensional, and there are some models like that, you have to plot all of what I told you here in 2 dimensions and see of appearance or disappearance of minima in 2-dimensional space.
Then can we see like more complex behavior?
Yes, exactly. But everything is rooted in this appearance or disappearance of saddle points. Okay? So this one, the saddle point, is splitting into 2 saddle points, and that's it. And here the minimal saddle point is just shifting from the right to the left. This is the major change.
One more question.
Yes.
Can we use this procedure to create pseudo-random numbers, or even really like actually random numbers?
Random numbers. Not exactly, because it's no, I don't think so. I have to think about it a little bit. But this idea of converging to a minima, so for example, you know all of this AI stuff, right? Chatbot, how eventually all the neural networks are trained. How the different neural networks are trained. Backpropagation. But what physically is over if it's the learning procedure is doing?
Gradient descent.
Minimize gradient, no. It minimizes a cost function. And what is a cost function? It's exactly like energy. Okay, so they have an effective energy in all those models of neural networks. They have an effective energy, and what they are doing is usually not 1-dimensional or 2-dimensional. It's million dimensional, and they're looking for a specific minima. All those algorithms, effectively, what eventually they're doing, they're looking for a specific stable point on a multi-dimensional surface, right? And once they reach that most minimal point, they usually say, well, it's the stable state, this is the equilibrium, and now the system have learned. So all the process of learning in computer science is of actually creating an effective dynamics on a multi-dimensional free energy. There are also entropy here and energy.
אבל אחת הבעיות שם שאתה כן יכול להיתקע על מינימום שהוא לא המינימום הגלובלי.
Exactly. So the question is, but maybe I am stuck in the metal stable state.
שם אתה יכול להיתקע, אין לך
Yes. So how the people in computer science solve the situation when I'm stuck in a metal stable state and not reach the global minima? They add a noise. And what is noise in physics? Temperature. So basically they heat up the system, effectively, in order not to get stuck in a biased solution which is wrong, right? For example, the ChatGPT will just curse you all the time, okay? So they add noise. It's a very physics-like problem of non-equilibrium statistical mechanics. All right. Now, given all of this, two people, Lev Landau and Ginzburg, and I forgot the name of Ginzburg, the first name. So they thought that, well, you see, we can create, the only thing that matters in order to describe phase transition, or in order to see what's going on in the vicinity of those critical points, the only thing that you need to know is what? How your free energy looks like. That's the only thing that's important. You don't care about what exactly is the physics, you don't care what exactly is the system, magnetic system, it's vapor, gas, it doesn't matter. The only thing that matters, and this idea propagated into all the other fields like evolution or computer science, is please provide for me the effective free energy of the system. And if I can describe to you the free energy of the system, I can tell you what's happening. Right? Now, for physicists, it's interesting. Is there a phase transition? What is the type of the phase transition? How universal is the phase transition? I don't really care about what's happening to the system over here, over there. The only thing that's important, and this is the universal law, maybe there are two minimas and they are switching from one to another. Maybe there is one single minima that's splitting. Maybe we are concerned with some higher dimensionality problem and there is something else that's happening. So the idea of Ginzburg and Landau is basically, let's try and explore the free energy in the vicinity of this critical point. Okay? In addition to this idea of free energy, they also see a lot of experimental data. And in this experimental data, they found out that near this critical points, especially the second order phase transitions, many different systems behaved exactly in the same fashion. I take a chunk of metal and I look what happens to it at this second order critical phase transition. And I take liquid gas, or for example like a van der Waals gas, and I look what appears to it near its critical point, second order critical point. The behavior is very similar. I'm looking on some glassy material near critical point. It's also going to behave very similar. So what they have suggested that there are universal features or universal form of this free energy near critical phase transitions. Right? And it's maybe not important. So what can change? The critical temperature can be modified. Some microscopic parameters can change the critical temperature. Yes, can be higher or can be lower. But the behavior of ordered parameter in the vicinity of this critical point is pretty much universal. That's what they've seen in experiments. And as we described over here, the only thing that's important in order to describe this critical phase transition is, well, how your free energy looks like. That led them to conclusion that in many systems, the free energy, at least in the vicinity of this critical point, looks exactly the same. It doesn't matter if it's metal, magnetic liquid vapor, or some tension properties. if you plot the free energy and you look exactly near this critical phase transition, it's going to be very much the same in all those different materials. Okay? So this is how they started their development of, let's think about it, the free energy. Universal forms. It's called Ginsburg-Landau theory. And critical exponents. So what they have assumed, as I told you, the first assumption is the form of this free energy is universal. So the only thing that matters are some global considerations. If I don't care if it's this type of metal or that type of metal or magnetic paramagnet material, the only thing that should be important are symmetries and energetic considerations. That's it. Okay? So that was their idea. If I'm only taking into account symmetry of the system and energetic considerations, so for example, that yes, it's preferable for any given spin to point out in the direction of the external magnetic field, those are the only things that matter, and this is why it's universal for all the many different systems. Okay? So they just say, well, let's expand, write an expansion of the free energy. Okay? Expansion of the free energy as a function of m in the vicinity of t equals Tc. So here they start, they say the following: this is my free energy. There can be a constant term, right? It's a function, so we start to expand it in some sort of a Taylor series. So there can be a constant term. Let's call it A. Okay. In addition, there's also going to be an additional term, right? What's this additional term? Let's call it H multiplied by M. And with a sign minus. Why do I have this term? So if I have H, let's call it H, big H, not small h. So if I have an external magnetic field, I know that the system will try to be in the direction of this external magnetic field, positive or negative. So it's going to lower down the free energy. Okay? Because I know that the equilibrium occurs for the minimal point of the free energy. So if if there is an external magnetic field, right, the induced magnetic moment should be at the same direction at the or the same sign of the external magnetic field. So we'll have a minus over here. Okay? And they say, well, I only want the linear effect of the external magnetic field. I want to push the magnetic field a little bit. Right? Not creating a huge magnetic field. It's basically a linear response. I'm applying a small external magnetic field, and I should expect a small change of this free energy due to the magnetic field that I applied. All right. Now, additional term. We should add a term that looks like B to the multiplied by M to the second power. Why we add this term? Well, we know that if there is no net magnetic field, okay, if there is no net magnetic field, so for H equals 0, we know that there is no preference if we take all the spins in the system and we change it to their negative sign. There is no preference. So if we have two spins, or and they're pointing in this direction. We shift everything, and they're pointing in the opposite directions now. Nothing really have changed inside the system. Why? Because there is no energy due to the external magnetic field, and we only have this coupling energy. So we have J, R, I minus Rj multiplied by Sri dot Srj. So if we change the sign of Sri, and we also change the sign of Srj, this coupling stays exactly the same, right? So there is no preference if I have this specific configuration or this specific configuration. So this is why everything should be symmetric when H equals 0. So we have this B multiplied by M squared. Now we can say, well, let's stop over here, right? This is our free energy. Let's stop here and see what happens. Why it's a bad solution? Why Ginzburg and Landau decided, no, we have to add Cm to the fourth. Why those two geniuses had to add this 4?
Why not the third power?
It's not symmetric.
Second derivative.
It's not symmetric. If I had a second, if I have a third power, it's going to be not symmetric. When I flip all the spins, so I cannot have it.
Why
Okay.
not have it dependent on H?
Because I'm only taking this term. This is the smallest term possible, coupling of H to M. Otherwise, it's going to be H to some power, M to some power. I don't want those terms. Okay? Minimal assumption. But if you think about, oh, I need minimal assumption, why not stop over here? Why those two guys, they said, no, no, no. The minimal form of the free energy, which is basically called the field theory, what we developed here, F is our field, and it's a scalar field theory. So why to add a fourth order to our free energy? Exactly. So if I have only the second term of M, it's going to be always a parabola, right? So if our free energy is only dependent on M up to the second power, the only thing that can be happening is that I have parabola over here, or I have parabola over there. It's going to be parabola. Always is going to be parabola, right? So I need an additional term in order to see some sort of transitions, right? So in all those systems, I do see transitions. So the minimal assumption is just, let's push by hand an additional term which is going as to M to the fourth, and there is no term that goes as M to the third, because then this guy is not satisfied. The symmetry of flipping the spins, right? So we have two assumptions. The system has to be a minimal effect due to the application of external field. Assumption number 1. Assumption number 2, symmetry of the system. And their claim, the claim of Ginzburg and Landau, is that if you include in this free energy all the additional symmetries that you have, it's going to describe very well your system. So here we do not have any additional symmetries. This is why we stop over here. Another thing that they said is that, well, I don't know what A is, I don't know what B is, right? But I do know what C is, or at least the sign of C. What has to be the sign of C? Can it be positive or negative?
Negative.
Why it's going to be negative?
So we have
Concave convex, remember? But it has to be positive. C has to be positive. Why does it have to be positive? Remember, this exactly. So the free energy eventually has to have a minimum, right? The system chooses the minimum of the system of the free energy, and this is where it's going to sit. Now, if we take here C, which is will have negative parts, okay, and we plot it as a function of, this is M, this is F, and if C is less than 0, so for very large M, this term is going to be dominant, right? This is M to the fourth. For very large M, this is the dominant part, and it does not care about M squared or M or the constant. Now, if this is the dominant part for large enough M, the sign of F for large M is going to be dependent only on this dominant part. So if C is greater than 0, it's going to be positive. If C is less than 0, it's negative. It's going to be negative. Now, if F is negative, somewhere over here or somewhere over there, it has no absolute minima, right? It has no absolute minima. The absolute minima is n goes to plus infinity or n goes to minus infinity, but this is nonsense because the magnetic moment of a single spin cannot be larger than 1 or mu 0, right? So this is an unacceptable situation. Any free energy, if we describe it like in this form, up to the fourth order, it has to have this limitation that C is larger than 0. When this limitation is just kicked out of the window, when we add additional terms. So we can have additional terms over here, and then there is no limitations for C greater than 0. Okay? But let us stop because it's going also to be complicated enough, so we'll stop at this term of m to the fourth, and we look only on the situation when C is greater than 0.
אבל אם נגיד לוקח n מאוד מאוד גדול, אז הייתי הולך לפלוס אינסוף.
No. When C is negative, you only get a negative part, negative f for large m or small m.
בגלל זה אין בעצם חזקות חיזוגיות, כי יש להם אחד עולה למעלה.
Yes. But also because of the symmetry.
אז זהו, את הסיבה הזאת לא הבנתי. אם זה חשוב, אז אני אשמח.
Okay, so the question is why don't we have m to the third? Okay, so let's assume that we're going to have to m to the third. If we have m to the third, and we don't have this part, okay, or we don't have this guy, right? We take h equals to 0, and we have c to m to the third, and we have d with m to the third, right? So our free energy is a plus bm squared plus dm third m to the third plus cm to the fourth. And the question is why I say d has to be 0, right? So the argument is when h goes to 0, if I take all the spins and I flip their direction, so any spin that was pointing up is now pointing down, and any spin that was pointing down is now pointing up. Okay? So remember the energy of the system is minus h dot mu 0 dot sum from I from 1 to n s r I minus 1/2 sum over I sum over j j r I minus r j s r I s r j. This was the total energy of the system. The probability of any given state is completely provided to us by the different energies that we have inside the system. Okay. So when h equals 0, I don't care about this term because it's simply 0. Okay. So the only thing that matters when h equals 0 is this energetic coupling between different spins. So what I'm saying to you, take any spin and flip it. So if it was +1, I'm going to give it -1. And if it was -1, I'm going to give it +1. What I'm saying is that when I'm performing this transformation, so any spin is going to be a negative, what is going to happen to SRI dot SRJ? It's going to transform into minus SRI dot minus SRJ. Right? This is the transformation that I perform. Minus and minus cancel each other, and it's equals to SRI dot SRJ. So by flipping all the spins, this is not going to change, right? The coupling constant is not changing, so the energy is going to be exactly the same. So the states are going to be, the different states are going to be represented by similar energies. So the free energy cannot be dependent on m to the third. Okay? Because what's happening when I'm flipping all the spins in the other direction? M from plus m0 going to minus m0. And the free energy, if there is a dependence on m to the third, is going to change. But we know it shouldn't. There should not be any term with m to the third power.
אז למה זה לא מפריע בחזקה הראשונה?
Because then h is not 0. All right. Only when h is not 0, then we have this term, and it indeed affects the energy of the system. This is true. But when h is 0, we don't have this term. The only thing that is interaction between the different spins, and the interaction between the different spins due to this transformation is staying the same. So the whole energy is staying the same, the whole energy is staying the same, the free energy should be exactly the same.
תאורטית היה יכול להיות איבר של h כפול m בשלישית.
There could be a lot of different stuff, but if you take m to the third, okay, it have to be coupled with h. This was his answer, question, yes. But I don't want any more coupling between h and m. I'm taking only the minimal one. Right? Okay, so what's going on? So this is our situation. Right? We used all the symmetries, we have written the free energy, and we start over here. So what happened to any system that has a free energy that looks like this? So the next step that we do, right, we say, well, we need to explore how this function is behaving as a function of m. Are there any saddle points? Are there any most minimal point that can change into less minimal points, so that there's transition from steady state to metastable state? We have to explore, like we did in like 9th grade or whatever, the properties of this function. Right? So if we want to understand something about the system, we plot f, right? At least the simple case, and we explore this. Right? Additional incentive why we should teach kids to explore saddle points of functions in high school. All right. So how this function looks like, we don't know, right? But let's take the derivatives. We want to say df to dm equals 0. Let's look for saddle points of this function. Okay, so what's happening over here? A does not care, so we have minus h plus 2bm plus 4c m to the third equals to 0. Okay, so it's basically 2bm plus 4c m to the third equals to h. So it's the third order. You look on this guy, right? It's a third order function, third order polynomial. So if we plot this, the function of m, the possible solutions are, it can go like this, right? It can go like this. Or it can go additional over here. It can go like this, or it can go like this. Right? So we see there is a transition for this function from a situation where we have 3 solutions, right? Exactly as we've seen in the Ising model. We have three solutions to a situation where we have only one single solution. Okay. When exactly this transition occurs, when exactly this transition from 3 solutions into 1 solution occurs? Mathematically.
C equals 0.
What?
C equals 0.
How I should look for it? Don't give me a final answer. I'm not sure that it's true. But how should I look to it?
Take another derivative.
Oh, exactly. So what is the transition? So you see this additional minima. At some point, we know that this additional minima will be above 0, and we are going to be left with only one solution. One solution is for sure happening. Why? Because if you look on this, you do the n to the third. This is the dominant part. For a large m, it's going to be very, very positive, and for a small and negative m, it's going to be very, very negative. So there is always at least one solution. The question is, there are 3 solutions or 1? We do know, because of the third power, there is up to three solutions over here. Okay? And we also know that when this additional minima is going to be above 0, or at least exactly at 0, right? This is when this additional solution, or this additional two solutions will appear in the for our free energy. Okay, so what we want to do is to take an additional derivative of this guy and see and look when this minima is below or above 0. Yes, questions? Yes.
Yeah. How do we model the situation when we have two-way solutions?
You don't have two solutions over here.
Yeah, but when the minima of the black one hits.
We'll come to that. So we will come exactly to this point when we have exactly two solutions, right? All right. So let's take an additional derivative of this guy. F. This is F. This is df to dm as a function of m. So now we're plotting as a function of m d square f to dm squared. What is the derivative? So we have 2b plus 12c m to the second power equals 0. Right? So very simple. What m equals to? M equals to what? Minus b divided by 6 divided by c square root, and we have to take both of the solutions, so plus and minus. Okay. C is positive.
B is negative.
B can be negative.
Must be negative.
Must be negative. Or
If it's negative, we won't get a phase transition.
or you can have something like this. So the sign of B's are going to determine what's happening, right? The signs of B are going to determine what's happening. So look on this guy, right? So what is happening? So it's m squared, and if I plot it, right, how it looks like? So it's a parabola. Okay, so it's a parabola. Okay, so those points are minus b, square root 6c, and square root of minus b of 6c, minus and plus. Okay, those are the 2 points. Now I'm going backwards. I'm going backwards and I'm saying, well, this is the negative part. Okay, so this attributes to this one. Okay. And this is the positive one. This is this maximum. And it appears at what? It appears at square root of minus b divided by 6c. And this guy appears at minus square root of b minus b divided by 6c. Okay? So we're only interested in when this minima, that we know exactly when it happens, okay, when it equals exactly 0. So let me write it down. So the transition occurs when 2b, right? 2b of square root of minus b divided by 6c plus 4c square root of minus b divided by what? By 6c to the third power equals h. Okay. So we can solve the solution, right? When this is exactly 0, when this is exactly 0, okay, this is the solution. This is for any h. H can be positive or h can be negative, but exactly when we solve the solution, we solve this, we find out what is the minima, or when this additional minima occurs, right? So if it's above 0 or below 0, this is the only thing that matters, because we try to solve this equation. Yes? Questions? No? Now, what was the most interesting point that we looked on previously? What happens when h equals 0? So there is indeed some specific transition. Well, but it somehow, well, if there is a minima or no minima, it's going to be dependent on this guy. And okay, so basically we have to check it, and then we have to. This is the 0 point, and then we can submit it into this equation, and we find all the different parts that we need. But what happens when h equals 0? Because the second order phase transition was interesting, right? We already do understand about this different behaviors of f as a function of h. There is a first order phase transition. The interesting point is this second order phase transition, because then we have no external field, right? We have no external field, and still we expect that somehow, by some miracle, due to interaction, self-induced magnetic moment will appear out of thin air. Okay, so we want to explore this, especially this situation, this for any h, but especially we want to explore what happens when h equals 0. Okay. So when h equals 0, we know that those are the two solutions, right? For this happens for any h. But let's look on this equation, okay? This df to dm equals 0 when h equals 0. Okay? So df to dm equals 0. And we obtain from here that it appears when 2dm plus 4c m to the third equals 0. Okay, we can take m out, m, and inside we have, or 2m, we have b plus 4 plus 2 c m to the second power equals 0. So out of this, we have our three solutions, right? Either m equals to 0, or m equals to plus minus a square root of minus b divided by 2c. Okay. Two solutions, one m equals 0, the other one m equals to plus minus of square root of minus b divided by 2c. And if we plot f, we start to understand what exactly is going on over here. So for h equals 0, this is m, this is f. And because due to the symmetry, so it's either we can have this situation, right? When there is only one solution, right? When we are going to have only one solution. When b is positive. C is always positive, right? C is always positive. So it's going to depend on b. Either we have one solution or three solutions, okay? So this is b larger than 0. Okay? This is the only case, because m cannot be imaginary. M is a real number. So C is larger than 0, 2 is larger than 0. If B is larger than 0, it's a negative number. Square root of the negative number, it's something that's imaginary. We don't have it over here. So B larger than 0, this is the only behavior that we see. But what happens when B is smaller than 0? Okay. So when B is smaller than 0, we observe this transition to double well that we've seen before. This is F. This is M. Okay, this is still H equals to 0. And we now have blue one. Three solutions. This is M equals to 0. Okay, and this one is plus a square root of minus b divided by 2c and minus a square minus b divided by 2c. Okay? Those are the only solutions that we have inside our system. Nothing other happens. So all the transitions that we now know are occurring where? Are occurring exactly at this point when b equals to 0. What happens when b equals to 0? This parabola is becoming simply very, very, very broad. Why? Because the first derivative is 0, okay? But when m equals exactly, or b equals exactly to 0, let's see what happens over here. B equals 0 over here. So the m equals only 0. We take another derivative. We still only have one solution. M equals 0. Okay? So basically, this is what we've seen before. The first order derivative is 0. The second order derivative is also 0. And also the third one. So we have a broad function that it still looks like a parabola. Okay? But only one single minima over here. Okay. So this is exactly what we've seen in Ising for this mean field solution. Right? Now, in order to understand what happened to this system, from this theory of Ginzburg-Landau, we only need to explore this free energy, which is pretty simple to obtain if you only consider some symmetries and energetic considerations. You want to explore what is going on at the second order phase transition in the vicinity of this b equals 0. Well, that's what we're going to do on our last lecture on Tuesday. Let's explore this region when b equals 0. And what are the interesting behaviors that we can obtain from this very simple f? Okay, so the only thing that is left, and all the behavior that one can obtain is by exploration of f equals to, we have a minus m h plus b m squared plus c m to the fourth near b equals 0. If we know how this function can behave and on what are the different behaviors we can pull out in this region when b equals 0, we know everything about the system near the phase transition. And their claim is, no matter what the system is, if you can write its free energy in this following form, all the systems will look the same to you. Okay. So we will have another 45 minutes on Tuesday.
But what is B?
What is B? It's 0.
No, but like physically, what does it mean?
They have a claim. It has to be TC. It has to be proportional to T minus TC, right? Because the transition occurs when? At the critical temperature. So it's T minus TC. כן, התיקונים האלה הם סרטונים, אבל זה אותם שיקולים אם יש לך גם ספרים אחרים.
פשוט אני אעשה את זה לאוכלוסייה.
את לוקחת